Welcome back to a brand new Explore Science with the Ward Beecher Planetarium. I'm Tiffany Woolbrick, and today we will be exploring light. There are so many things we could talk about when it comes to light, but we're going to be focusing today on a specific area of science and astronomy called spectroscopy. Spectroscopy is the process of breaking up light into its different colors to learn more about the light source. Light has information, it's trying to tell us something, and spectroscopy helps us understand that. For example, this white LED that you're seeing up here, this white light, you may see the color white. Our brain interprets it as white, but this is actually all colors of the rainbow shining at the same intensity or brightness. So if we see a light source that looks white, it has all colors of the rainbow, and our brain simply interprets that as the color white. But what about these other colors? How are they created, and what are they trying to tell us? We'll learn a little more about this today. And I think the best way to understand light and why it acts the way it does is to think about light as a wave. So to demonstrate this, I've got one of my favorite toys, a Slinky. We can create waves with Slinkies, right? I can stretch my Slinky out, but it doesn't look much like a wave right now, does it? What do I need to do to my Slinky to make it look like a wave? I have to add energy to it. So I'm gonna move my hand up and down, adding energy to our wave, and you can start to see those peaks and valleys that make that wave shape. Now, if I added more energy to my Slinky, there we go. We can start to see maybe more than one of those waves. Adding a whole lot of energy there. So in the same length of Slinky, we can actually see two peaks and valleys there. So light does this, and it corresponds to different colors. So if we talk just about the visible spectrum, or the visible light that we can see, the red side of our rainbow, that color has a longer wavelength. It's a lower energy wavelength, like this. Okay, that would be the red side of our rainbow. The purple side of our rainbow, or the violet side of our rainbow, those are very energetic waves. So we would have something more like that, right? So with the same length of Slinky, you see more peaks and valleys. And it's important to mention that light is so much more than what we can see. Our eyes as humans can only see a teeny tiny piece of the whole light spectrum, which is something we'll get into a little more later. But I wanted to invite one of my friends to talk to us a little bit more about how astronomers specifically use this science, spectroscopy, to understand our universe. So I'd like to introduce you guys to our planetarium director, Dr. Patrick Durrell. Hi, Dr. Durrell.
Hello.
So we're here to talk about light. We see light in different colors, right? We can see it in white light, but we can also see different colors. And it's my understanding that there's light waves out there, or there's light out there that we can't even see. That light is so much more than just the colors that we see around us.
Yeah, well, the thing is, what light is really, at its most basic, it's a series of interconnected magnetic and electric fields. And so that's why we call light in general electromagnetic radiation. It's a bit of a mouthful, but when when we say light, we mean electromagnetic radiation. Now, the thing is electromagnetic radiation can act like a wave. So the size of the wave, so if think of a wave like this, the size of the wave dictates what type of electromagnetic radiation it is. Your eye is a very good receptor of light, but of a very small range of wavelengths. Okay, so the colors that you see in the outside world are light that comes into your eye. Your brain registers it at certain colors, and you can see a beautiful sunset or the green leaves on a tree, and all sorts of wonderful things. But there are many smaller and bigger wavelengths of light, which have different energies, that your eye cannot pick up. And so there's lots of kinds of light out there that you can't see. They're out there, the universe is filled with it, but you can't actually see it. And some of those light have different names. You may have heard of ultraviolet radiation. Okay, this is why you need to wear sunscreen at the beach, is because of UV rays coming from the sun. Your eye can't see them, but your body can feel it. Okay, radio waves are a type of light. Infrared, okay, your remote controls. Infrared radiation. Again, your eye can't see infrared, but you can build detectors that can sense it. So there's all these different kinds of light that you can't see. But there is that narrow range of energies that your eye can see, and we call that optical light.
Or visible light, that's where we get all the beautiful colors that we can appreciate. I see you're in the planetarium today, and you have some light tubes set up here. Do you want to explain what you've got going on in the planetarium?
Yeah, well, I want to demonstrate one of the important techniques we use. Astronomy, unlike most other sciences, is a very remote science. So how we study almost everything in the universe is from its light, whether it's reflected sunlight that gets to us from the moon, the light from Jupiter, the light from a nearby star, the light from a distant galaxy. So an important part of astronomy is being able to collect light and dissect it into the different wavelengths of light so we can see what's going on. What I have here are 3 gas tubes. These are little glass tubes that have little bits of gas in them. I've got one that's hydrogen gas, one that's helium gas, and one that's neon gas. And these tubes, the job is the electricity will heat up the gas, and the gas will actually glow. And that glow is simply, the atoms, as electrons in the atoms are falling down, and different gases emit at different wavelengths. And we use that to fingerprint what things are inside of stars. So we don't have to visit a star with a sample collector and collect star stuff to study it. We can actually study it from far away by collecting the light and running it through a spectrograph or a spectrometer. And I have here a little one. And the idea of a little spectrometer like this is the light comes in, okay, and the spectrometer splits the light up into all the different colors, and we can study all those different colors to tell us one thing, for example, what the gas is made out of. I'm going to turn on the hydrogen lamp. Now again, the reason I start with hydrogen is because it's the most abundant gas in the entire universe. Okay, so hydrogen is really one of the first steps in understanding astronomy. And with the electricity, you can see it glows a rather nice pink color. Okay, so why does hydrogen glow pink? Well, we're going to find out with the spectrograph. What I've done here is I've now turned on the hydrogen lamp, and this is the pink line that you see on the far left-hand side of the screen. Okay, the nice, beautiful pink color of the hydrogen lamp that's been heated up. However, on the left-hand picture, what we want you to look at are these little lines to the right. This is the light from the lamp has gone through the spectrograph, and all of the light, all of the energies that make up the pink light have been split up into these, what we call spectral lines. Okay, and these bright lines are at very specific energies. Okay, and the 3 big ones that you can see here is there's a red line. Okay, so this is at a specific energy and wavelength that your brain thinks is red. Then you've got a really bright cyan line. Okay, and then if you look carefully to the left of it, you can see a little purple line. Now, the thing is, this is the characteristic spectrum of hydrogen. And these lines have very specific wavelengths that astronomers can measure. And we know these ones very well because so much of the universe is made up of hydrogen gas. Now, how astronomers actually look at a spectrum is not quite just looking at the nice pretty lines, is we actually make a plot on what we show here on the right-hand side. Okay, so what you're seeing on the left, we've now plotting on the right. And all you need to know here is the numbers at the bottom correspond to the actual wavelength. Okay, and then intensity, so now how bright the light is going upwards. And what we want people to notice is that you can see these bright fingers sticking up. These are the spectral lines of the hydrogen lamp. So this one here is very specific to hydrogen. This is the red line. This is the cyan line. This one's the purple line. And I have a hard time seeing it on the left, but look, we can see another purple line as well. And this is the fingerprint of hydrogen gas. All hydrogen gas will have these 4 lines at those 4 energies. So if we see them in a nebula, or we see them in another gas cloud in another galaxy, for example, we can then use that information to say, oh, there's hydrogen in the gas. Now next in our arsenal is helium. And yes, this is the same gas you put into balloons and the same gas that makes your voice sound funny. It's the second most abundant gas in the universe. So it also makes up, a significant fraction of gas in stars. But what we're going to do is we're going to look at helium with the spectrograph, and we're going to notice that the spectral lines are a different number in different places. All right, well, this is the second tube. This is helium. Okay, it's a very bright white color if you look just at the lamp. And if you look on the left-hand side, you'll see the helium lamp itself. Now again, what we're doing is we're putting the light through the spectrometer, and as a result, all of the energy and wavelengths of light that are in this lamp get spread out over to the right, and you can see a different set of bright lines. So this already looks different from the hydrogen lamp you just looked at. Okay, you see a bright yellowish white line, a faint cyan line, a kind of bluish purple line, and an even more purple line to the left of it. So this is the fingerprint, the signature of helium gas. And all 4 of these lines have different wavelengths and energies than what you saw in hydrogen. Indeed, every gas has its own signature set of lines that we can use. Now again, on the right-hand graph, all we're doing is just making a plot of what you see on the left, and you can see the 4 bright lines like this picket fence. So this one here, this is that yellowish white line, which is really strong, okay? And then here's the cyan line, the blue line, and then the very purple line. So again, when astronomers take a spectrum with a large telescope somewhere of a nebula, okay, and there's various kinds of nebulae out there, they can actually see if there's helium present by looking for these signature lines. And our final example, this is going to look really bright to everybody at home. This is a neon lamp. This is a little gas tube filled with nothing but the gas neon. Okay, and you can see the rather unmistakable orange color of neon. And again, it looks different than the other 2 lamps that I showed you. And what we're going to find out when we look at it through a spectrograph or a spectrometer is that, again, it's going to have different sets of lines. All right, so what we have here is the neon light, which is rather bright, and it might be a little overpowering. And you can see the nice orange glow on the left-hand side of this screen. However, what you see on the right is the splitting of the lines, that all of that light from neon is going through the spectrometer, and it's getting split up into all the little wavelengths of visible light. So anything from blue, green, yellow, orange, all the way through red. And what we see here on the left is we see a lot of yellow and orange and red lines. Now on the right, this is a trace of the wavelengths, the sizes of the wavelengths of those lines. So this is the kind of spectrum that astronomers would use. And what you see here on the right-hand side is a lot of these little points sticking up. These are what are called emission lines. And these emission lines are specific to neon. So this is what we call our fingerprint. Okay, so these orange lines here, okay, there's a red line here and some of the yellow lines here. So when astronomers look at other objects in the universe, they basically have a long list of, well, what line is at this wavelength? Well, oh, that looks like a neon line. So this is how we can fingerprint stars without actually taking their fingerprints.
Wow, that was fascinating. So not only can we break up white light into its many different colors, but that those light sources have information. They can share information with us. And I've always found this area of astronomy fascinating, that we can use light, and by breaking it up in this process, we can learn more about the universe. You were mentioning there were some nebula out there that we study and understand through spectroscopy.
There's all sorts of things that we can do. I mean, a spectrum, like we've been showing you, is one of the most important tools that astronomers have in deciphering the universe. So whether we look at the lines in the picket fence to see what gases are in a nebula, for example, like the Orion Nebula, which is something you can actually see with binoculars in the wintertime sky. But we can study what materials are inside of stars. We can study, what constitutes the stars in galaxies. Okay, people can even use a spectrum to figure out how fast things go. So when astronomers look for really hot gas buzzing around a black hole, they can take a spectrum and learn all sorts of things. So some of the most wonderful things that we've learned in astronomy aren't just from the nice pictures that you see from telescopes like the Hubble Space Telescope, but come from astronomers being able to dissect the light from a source a long way away and use that information to learn a lot more.
Wonderful. Well, thank you so much, Dr. Durrell, for joining us today on Explore Science, and we hope to see you soon.
Absolutely. It's been my pleasure.
For today's at-home experiment, we are going to make our very own spectroscope. With just a few materials that are probably lying around your house, we can make our own spectroscope and begin breaking up white light into its component colors and studying that light just like astronomers do. All you'll need is paper towel roll, a pair of scissors, some tape, any kind of tape will do, a dark piece of paper, mine's dark blue, but you can find black or whatever dark color paper you can find, and an old CD. An old CD you won't need anymore. That's all you'll need. Okay. Now to make your spectroscope, the first step is an optional but very fun step. So I do recommend decorating your spectroscope. This is my complete spectroscope here. Okay, so you can paint it, you can put stickers on it, whatever you want to do on the outside of your paper towel roll. After your paper towel roll is done being decorated and it's dry, you'll want to make some cuts into your paper towel roll. This is where you might need parents to help out. Okay, I've marked on my paper towel roll where you will need to make your cuts. The first one is you're going to need to make a fairly large, I think it looks kind of like a tent shape cut in your paper towel roll towards the bottom. Okay, and then on the other side, you'll need to directly across from where you make that cut. So directly on the other side, you'll need to cut out a rectangle hole. This will be your viewing hole. Okay, so this is where your CD will set into your spectroscope, and this is where you will look at your light. Okay, and then the last thing, you'll need to cut out a circle from your dark piece of paper about the size of the top of your paper towel roll, and then you'll want to cut a little rectangle hole out. This is where your light sample will come in. We don't want light coming through the whole paper towel roll, we just want a little slit. So just a small sample of light. And that's what we're doing here. So then you just tape that on the top, you stick your CD in, and you have a spectroscope. This is what it looks like. I've taped my, my dark piece of paper on the top of my spectroscope. I slide the CD into my little slit on one side, and then on the other, I view the light. So light comes in from the top. You'll want to point the top of your spectroscope to your light source. It will travel down, be broken up into its component colors by the CD, and then you can view it in your little viewer hole here. That's all it is to it. Very, very simple. Just point the top of your spectroscope to your light source. You can do this with your fluorescent lighting in your house, maybe a neon sign if you can find something like that. Candlelight looks pretty cool. So any light source that you can think of, go and explore and see what looks different. Let us know in the comments what light sources you found and what you've observed in your brand new spectroscope. Thank you for joining us today, and remember to keep exploring.